What happened in the first few minutes of our universe? More than 50 years ago, physicists found that in that hot and dense early environment, nuclear reactions formed the two most abundant and light elements in the cosmos, hydrogen and helium. Those two elements constitute more than 98% of the normal matter that we observe in the cosmos today, mostly in the form of stars, galaxies, and intergalactic gas. Let us see how the creation of those two major elements occurred. We know that our universe is expanding today, since we observe that most galaxies, except our closest neighbors, are moving away from our own galaxy, the Milky Way. In the past, they were obviously closer together, and the universe was denser and therefore hotter, since we know that a gas that is compressed is also heated up. And we find that the universe reached extremely high temperatures and densities about 14 billion years ago, much higher than in the center of the Sun. In that extreme environment, known as the Big Bang, matter could not exist in the form of atoms and molecules of the various elements that we see around us on Earth. It was rather in the form of a hot and uniform soup of elementary particles. Neutrons, protons, and electrons bathed in a sea of high-energy photons of electromagnetic radiation. Countless collisions, in fact nuclear and electromagnetic interactions between those particles, maintain their numbers in equilibrium, which means that each particle disappearing through some reaction was immediately replaced by another particle of the same kind through the inverse reaction. But in the rapidly cooling universe, reactions became slower, and some of them ceased altogether, favoring the population of some particles at the expense of others. Thus, for every billion photons, there were about 7 protons and electrons and 1 neutron left when temperature dropped around 1 billion degrees. The thermonuclear fusion of a neutron and a proton gives rise to a composite particle, the nucleus of deuterium. But this nucleus is rather fragile, and it was immediately broken to its constituents by the energetic photons. Only below 1 billion degrees did the fury of the photons calm down. The nuclei of deuterium could exist safely now, and capture in their turn other neutrons and protons to form heavier nuclei, like helium-3 and helium-4. The synthesis of even heavier nuclei was impossible in those conditions, because those with 5 or 8 particles are completely unstable and do not exist in nature. Only some tiny amounts of the next lightest element, lithium-7, managed to form before the temperature dropped below 800 million degrees, after about 3 minutes, and primordial nucleosynthesis came to end. Essentially, all the neutrons of the initial mixture were thus found in the form of helium-4, the most robust of the light nuclei. For every 14 protons and 2 neutrons, 1 helium-4 nucleus was formed and 12 protons remained. Since neutrons and protons have similar masses, this means that at the end of nucleosynthesis, 1/4 of the normal matter of the universe was in the form of helium, and 3/4 in the form of hydrogen. This is indeed observed in some of the oldest gaseous clouds in the universe. The theory of primordial nucleosynthesis makes also precise predictions for the abundances of the other light nuclei, deuterium and helium-3, which are produced by tiny amounts, and these predictions are again confirmed by observations. In fact, the unique conditions during the Big Bang, such a large amount of neutrons mixed to protons, are never encountered during the subsequent evolution of the cosmos. Deuterium can only be produced in the early universe. The exploration of the ashes of the Big Bang by nuclear physicists and astronomers gave full support to the model of the hot early universe in the last half-century. Hundreds of millions of years after the Big Bang, the first stars would appear from the condensation of primordial gas clouds made of hydrogen and helium. Those stars and subsequent stellar generations would progressively produce all the other elements of the periodic table over billions of years. Now, most of our body is made of water. Its molecule is composed of 2 hydrogen atoms and 1 oxygen atom, which is 8 times heavier than both of them. Thus, hydrogen makes 1/9 of water. and a few kilos in each one of us originate from the hot early universe of the Big Bang. This part of our body is almost 14 billion years old as the universe itself. The making of more complex elements, including those required for life, like the oxygen we breathe, the calcium of our bones, the iron in our blood, during the billions of years of galactic evolution, is the topic of the next video of Astronuclear Nibbles.